We are given a geometric progression with a first term A, a common ratio R, and a sum to infinity S. We also have a geometric progression. Let's look at the first geometric progression. Let's say this is the first geometric progression, GP1. First term is A, the second term is AR, since R is the common ratio, and the sum to infinity is S. Sum to infinity is A over 1 minus R. That will give us one equation. A second geometric progression, suppose this is given by GP2. First term is A, the common ratio is R. So the second term is A uppercase R, and the sum to infinity is 2S. Sum to infinity is A over 1 minus the common ratio, but this is 2S. That is equation number 2. Part A, you need to show that little r is 2r minus 1. What we could do is we can substitute equation number 1 into equation number 2. So we are going to take this part, since this is S, and substitute into this S here. Upon substitution, we have 2 A over 1 minus R. That is A over 1 minus R. On the left, we have 2A over 1 minus R. On the right, we have A over 1 minus R. And we can cross multiply now, so that 2A 1 minus R is A 1 minus R. This big R and little r is, forget about the A. They cancel to be a 1. So that you have 2 minus 2R on the left, and we have 1 minus R on the right. We need to isolate little r. So we are going to rearrange this, move little r over, and everything else on the left goes to the right. So little r is 1 minus 2 plus 2r, and we have little r equals 2r minus 1. This is what we are asked to show in part A. Part B, it is now given that the third term of the first progression is equal to the second term of the second progression. The third term of the first progression is the second term of the second progression. Third term is given by AR squared. Second term is given by AR for the second progression. So let's just ignore A, they cancel to be a 1. We see that the square of little r is uppercase R. Part B, you are asked to express S in terms of A. So either from equation 1 or equation 2, S can be written as A over 1 minus a common ratio. To express A in terms of A alone, that indicates that we need to find the value of the common ratio, either the big R or the little r, doesn't really matter. But from this part, we know that little r is 2r minus 1, so we substitute it into this equation, so that 2r minus 1 squared is r. Now expand this, we have 4r squared minus 4r plus 1 equals r, and move that r over, so that 4r squared minus 5r plus 1 equals 0. We have a quadratic equation in terms of r, which can be factored to be 4r and r. Last term is a 1, both are negative. Then either 4r minus 1 is 0, or r minus 1 is 0. Isolating r, we have r equals 1 over 4, or we have r equals 1. For the geometric progression to converge so that we have a sum to infinity, this is not possible. Because the absolute value of R must be less than 1 for the geometric progression to converge. We only have R equals 1 over 4. Then from equation number 2, 2s here is A over 1 minus 1 over 4, so that 2s is A over 3 over 4, that is 4A over 3. Then s here, to isolate s, we divide by 2, we have 2A over 3. So we have written s in terms of A.